Hello everybody. In this video I want to talk about the quotient rule and basically just proving it with no applications or examples. We just want to go through the proof. So that's what the quotient rule says. It says if g of x equals m of x over n of x, then g prime of x will be the derivative of the numerator times the denominator minus the derivative of the denominator times the numerator all over the square of the denominator. So I wanna, normally they prove this by using the chain rule and the product rule, but I want to prove this by using first principles, which is what most lecturers avoid because it can be a little bit more involving. There's too much work involved, but not complicated, simple. But let's go through it then using the first principles. So the proof is as follows. We are told that g of x is the quotient m of x all over n of x. We can say therefore g of x plus h then will be equal to m of x plus h all over n of x plus h. Let's go to the definition of the derivative from first principles. We know that it says g prime of x is equal to limit as h approaches 0 of g of x plus h minus g of x all over h. Substituting the two expressions in there, we have limit as h approaches 0 of this expression here, m of x plus h minus n, all over n of x plus h, and then minus m of x all over n of x all over h. So this is basically what we have. Now, how do we go about this? Remember I told you in the previous video that here we have both the special one and the special zero, or the special zero and special one. We have to rewrite this. So rewriting this expression, we go about it as follows. Let me move back a little bit to here. This will be equal to limit as h approaches 0. We start with the special one, and I'm going to take h to the other side and bring it back at a stage. So we have m of x plus h all over n of x plus h, and here is a special one times, I'm going to multiply now the two. I'm going to take note of this. I'm going to take, not multiplying at the beginning, but I'm going to multiply here by n of x and here by n of x. That's your special one. And this side, I'm going to multiply by n of x plus h down and in the numerator and in the denominator as follows. So here we're saying times n of x all over n of x. That's your special one right there, because that's one. We're multiplying and dividing by the same number. That's your special one. Minus, we're coming here and we're saying m of x all over n of x, and I have to multiply this one by that part. So you're multiplying the whole of this by that and the whole of that by that. So I'm going to have n of x plus h here all over n of x plus h. There's your special one. And remember this, that we have to multiply this by 1 over h there, because otherwise it becomes too complex. Now that we have the same denominator, then we can put the numerator together. So let's go to page number 2. There's page 2 here. Yeah, I hope you can see it there. All right. Let me move back down a little bit. That's right. So this is going to be equal to limit as h approaches 0 of what? Of m of x plus h times n of x minus m of x times n of x plus h. Like this all over. And if you like, you can bring the h down now. It will be n of x plus h times, what do we have there? We have n of x and times h down there. That h can now be brought down there like so. Now, so now we have to introduce the special zero. We're done with the special one. Now we must introduce the special zero in the numerator. So I'm going to have now, let me move down a little bit further down. I'm going to say this is going to be equal to limit as h approaches 0 of what? Of, now I'm going to multiply the 2 and add and subtract. So m of x plus h times n of x, and then I'm going to say minus m of x times n of x plus m of x times n of x. There is your special zero right there. Special zero. In a few steps back, I didn't write special one, but you will remember that. And then I have minus this term here now, m of x times n of x plus h. And remember, that is our numerator. We're dividing the whole of that by n of x plus h times n of x times h, like this. Right, now I'm going to use term-wise division, first factorize, and then use term-wise division by h. So factorizing the numerator, I have limit as h approaches 0. In the numerator, you can see there, the common factor is n of x there. So I'm going to have, if you like, I'm going to have n of x. Let me use curly brackets inside this time, m of x plus h, that part, minus m of x. That's factorizing these two terms, and then I have a plus sign there. But what I'm going to do now is I'm going to take my common factor. You can see the common factor is m of x there, but I'm going to take minus m of x as my common factor. So minus m of x, and when I divide minus m of x into this part here, it's going to give me positive n of x plus h. And then that one there, if I divide this into that term there, it will give me, if I divide this into that term, remember this into that term there, it gives me that, because these cancel, you have that. But this into that term there, you're going to get minus, because positive divided by minus is actually minus. So it will be minus n of x. Please check your algebra there. Right, and then I have, doing this one step at a time, I have n of x plus h times n of x times h. Now, it's time for me to use what we call term-wise division. Now, I'm going to take the h up. So this is going to be limit as h approaches 0 of, take note of this. I'm going to have n of x, and I'm going to use the curly brackets there, m of x plus h minus m of x all over h. And then I have minus, and then I have m of x, and then I'm using curly brackets, and I'm saying n of x plus h minus n of x all over h. And in the denominator now, I have n of x plus h times n of x, like so. Now is the time for me to take the limit in the numerator and in the denominator. So this is going to be, please take note of the property of limit. So this is going to be limit, I'm up there now, limit as h approaches 0 of, if you like, I can put, yeah, I'm going to go into numerator, of n of x times, I'm there now, curly brackets, limit as h approaches 0 of m of x plus h minus m of x all over h, like so. And then I'm going to say minus limit as h approaches 0 of m of x times, I go up and I take limit there also, limit as h approaches 0 of n of x plus h minus n of x all over h And then I'm going down into the denominator now, and I do the same. I'm going to take limit there, limit as h approaches 0 of this part here, which is n, let me rewrite that, n of x plus h, and then I'm multiplying that by limit times limit as h approaches 0 of n of x. Remember here I said we have to have a limit as h approaches 0 of n of x plus h, like this. Right, so limit in the numerator of that term, that term, that term, and that term over limit of that term and that term. So now let's see what we get. So we're going into the numerator now. This is unaffected by h. As you can see that there is no h there, so it remains n of x. And this part here, you can see that's exactly m prime of x, that part. And then I have minus. This part here, you can see this is unaffected by h because it's m of x. There is no h there. It's just m of x. So it remains m of x. And this part here, you can clearly see that this is n prime of x times n prime of x all over. As h approaches 0, this part approaches n of x because h approaches 0, and then you have only x in there. It will be n of x times, this is unaffected by h, so limit as h approaches 0 of that remains n of x. Now, if you simplify this, you get exactly what we're looking for, which is n of x times m prime of x minus m of x times n prime of x all over the square of the denominator, which is n of x squared. There, you can see these two terms are the same. So basically, this would be the end of the proof. Nothing special except for the special 0 and special 1, but nothing special. And if you check here, from here, it flows very nicely. It becomes a little bit complicated in terms of algebra when we have to take the h up there, but this is true because I've told you that term-wise division applies when there's a minus sign there or a plus sign. So we do have that. So we can divide h into the numerator there, and in the denominator we're left with only that. And going through the calculations, that's what you have. So this is the proof of the quotient rule by using first principles. On rules of differentiation, I am going to, in my next video, talk about, not next video, perhaps the video after the next video, I'm going to take a pause a little bit on this stuff, and then I'm going to come back with a chain rule. Most of my students have been requesting me to cover some work on integration, and I'm one that likes to build the concept and then develop it. So we'll see, because we have quite a lot of work at this stage. If you're new to the channel, please subscribe and invite friends to subscribe to this channel, and let's share these videos. And I believe that if you give us the support, we have no reason not to give you the support to achieve academic excellence. All right, God bless. See you next time.